Hello, this video explains the process we follow to make the Puzzlebot respect a traffic light. The robot had to detect red, yellow, and green signals using its camera, and then modify its motion according to the detected color. The spec behavior was stop on red, move slowly on yellow, and continue the planned path on green.
To achieve this, the system was implemented in ROS2 using four main nodes. The camera publishes raw images to the color detector. The color detector publishes the detected traffic light state. The odometry node estimates the robot pose using encoder data. The path generator publishes the desired waypoints, and the closed loop controller uses the odometry and the goal position to generate velocity commands for the robot.
The first implementation step was the color detector. The node subscribes to the raw camera image. Each frame is resized to 640 by 480 pixels to reduce computational cost while keeping enough resolution to detect the traffic light. Then, the image is converted from BGR to HSV, color space, because HSV separates color information from brightness, which helps with color segmentation.
After converting the image to HSV, color thresholds are applied for red, yellow, and green. A region of interest and zone-based segmentation are used to reduce false detections. Morphological filters remove noise, and the dominant color is selected based on the largest detected area.
The next step was the odometry node. This node subscribes to the right and left encoder velocity topics. Using the differential driver model, the linear velocity is calculated from the average wheel velocity, and the angular velocity is calculated from the difference between both wheels. Then the Euler integration is used to update the robot position in x and y, and its orientation theta. This estimated pose is published on the odometry topic and is used as feedback by the controller.
The closed-loop controller receives the robot pose and the target waypoint. It computes the angle and angular error, normalizes it, and applies proportional controller to generate angular velocity. The robot first aligns with the target and then moves forward while correcting its orientation.
The traffic light logic was implemented inside the controller as a finite state machine. The states are stop, align, move, and wait for green. The traffic light condition has priority over the navigation states. If red is detected, then the robot enters the wait for green state and sends zero velocity. It remains stop until green is detected again. If yellow is detected, then the controller reduces linear velocity. If green is detected, the robot continues following the waypoint sequence.
The path generator sends waypoints sequentially, publishing the next one only after the previous is reached.
The system was tested under four different lining conditions. In all these scenarios, the robot successfully completed 4 out of 4 waypoints, achieving 100% completion. The experiments were performed using a 1 by 1 meter square trajectory. Since the traffic lights were printed, one team member manually switched between the red, yellow, and green signals during the execution. The main difference between the scenarios can be observed in the trajectory accuracy, which varies depending on the lining conditions, as is shown in the following videos.
Performance was evaluated using waypoint completion and position error. The robot achieved 100% completion, but the error increased from 0.0087 meters in low light to 0.0511 meters under strong illumination, showing that lighting affects perception and accuracy.
In conclusion, the system is functionally robust since it successfully completes the task in all test scenarios. However, the accuracy of the robot is limited by the vision system, especially under variable lining conditions. This indicates that the system is perception limit rather than control limit. Future work includes implementing adaptive color thresholds, improving lining robustness, and integrating more advanced control strategies to reduce error accumulation.